All right, welcome back. So we're in project 6 where we're going to be reducing noise by strategically reducing the vocabulary. So what we've done is we've taken these metrics that we've kind of used earlier as like a heuristic to see whether idea was a good idea, and we're going to use it to carve out a little bit of the noise so that the neural net can better see the signal. Now in this case, most of the action happens in this pre-processing step, right? So instead of we kind of updated the training before. Here, we're going to try to reduce the vocabulary, which is this vocab object, which gets turned into the word to index object and used to create our indices. We want to reduce this in specific ways according to different cutoffs and thresholds. So in this case, I created a polarity cutoff and a min count cutoff. Now, what the min count cutoff does, it says, okay, so in order for a word to be included in the review vocab, when I was creating the vocab, it has to exceed a minimum count. All right. So if it doesn't get in the vocab, it doesn't actually get trained on according to the pre-processing step down here. So right, if the word is not in the vocab, it's not in word to index.keys, it doesn't get it added to this indices list, it doesn't get trained on, so it gets ignored. So that's the first thing. And the second thing is this polarity cutoff. This is saying that this pos-neg ratio has to be greater than or equal to the polarity cutoff, or less than or equal to negative the polarity cutoff. Because if you remember, this thing centers around 1. So we're saying a word has to either be less than the negative ratio or more than the positive ratio, right? So it's excluding this really tall and yet irrelevant section in the middle. So that's the idea. One other thing I did was I required there to be a minimum count for this positive negative ratio to really take effect. And the reason I did that is that occasionally you have really infrequent terms that have very little correlative power or a lot of correlative power, but they only happen once or twice. So the metric, it's a simple rule, it's a simple cutoff. I can't have it, be, oh, it's perfectly positively correlated, but it only happened once, right? So in this case, I found that this was a good number. So those are the two thresholds. There's not really a right way or wrong way to do this. Again, we're trying to cut out the noise, and this is different for every data set, right? So you're going to encounter a new data set, you're going to try to take a neural net, you're going to try to frame the neural net a problem where it can succeed at a data set. This is just the method that you go about by framing the problem when you're in a new domain. Like, these are not hard and fast rules. These are techniques to be able to make sure that your neural net has the best chance to capture new and interesting patterns. So all of this is the same. None of this has changed at all. Testing is not different. Running is not different, other than the resulting vocabulary is smaller. So let's give it a shot. I'm going to set the min count at 20 and the polarity cutoff at 0.05, which is a really small polarity cutoff. Like, this doesn't cut out too much of the vocabulary, and we can be more aggressive about it later. And yeah, we'll see how this thing goes here in a second. So what it's doing right now is it's calculating all those statistics as it started. So when you created, I had it do it then, and it's going to start training. So yeah, when you call the constructor, it calls preprocessed data, and preprocessed data runs all these statistics from before to help kind of identify signal. Look at the train. All right, very good. So this is actually a little bit of a speed lift from before. Not a lot, just a little bit, because we've reduced our vocabulary size. Then we look at our testing data, 85.9. Not a huge lift, but a small and significant lift. And you can pick your battles, and I didn't tune this for too long, so you kind of keep playing with this min count and polarity cutoff, and find which one seems to work the best for you. Now, the other thing I wanted to show here is that if we take this and just, crank it up, right? So if we set this to be more like, I don't know, we'll keep the min count the same, we'll set this to be 0.8, where we really carve out the middle of this guy. Like, we're just gonna take a big chunk, like 0.8, that's like right here to right here. And we're gonna say, you know what? This stuff has a little correlation, but I just think it's ambiguous, so just carve it all out. And we say, okay, we're going to train on that. Then we can really crank up the speed of this thing, the speed by which it trains, with a relatively small effect on our testing accuracy. And so sometimes, you'll find that this can be beneficial for two reasons. For some problems, you want to be able to train on so much more data. You want it to be able to run a lot faster. Let's see how much faster it goes. Training. Oh my gosh, look at that. So 7,000 reviews per second. It trained the whole thing in a couple seconds. And let's see what the damage is on the test. 82.2. So we lost 3%. Not bad. Like, we got a 7x increase in speed for almost 7x for a 3% decrease in quality. Now you're going to find it with neural nets. There's usually a speed trade-off quality. The only time that I know of when there consistently isn't is when you can reduce noise, because reducing noise tends to reduce the amount of data that you have to process, which increases both speed and accuracy. That's why I like it so much. But this can actually be really beneficial. One, for production systems, right? When you just need something to fly, to get through a ton of data, to really solve a real-world problem that exists out there, like the most laboratory kind of sterile, highest possible score isn't always the best answer. Sometimes the best answer is, hey, we want to fly through 1 million medical reports a day so that we can save the most lives. Give me something that's faster. And this is something that you can do to try to do that. And once again, we got almost a 10x. And if we cranked it up even further, we probably could. And yeah, so like the cool thing about this is that the more you carve out, you're saying, okay, I need to go faster, and I'm trying to do the minimum amount of damage that I can to go faster, right? So I'm getting rid of the terms that are most ambiguous in my prediction, and it's saving me lots of time. So now, why is it saving me time? Well, we do fewer sums. When we have fewer terms, we do fewer sums into this weight matrix, and we do fewer backpropagations into this weight matrix, or excuse me, this one, because there are fewer words in the review that we allowed to pass through that were candidate words that we could train on. And so that's just all we did, and fortunately, it increases the speed very significantly. Now, the other reason that sometimes people will increase the speed like this, or in a variety of other ways, is if you have so much training data that you could never train over all of it. It turns out that being able to run faster over more data, even if you choose a more naive algorithm or you're eliminating a lot of stuff, makes the accuracy really, really high. The most famous example of this that maybe people don't know is taking this effect is word2vec, right? So word2vec is a close approximation of other language models that people have been training forever. But the problem was the other language models took like a month to train on 1 billion tokens. And even then, it wasn't making as aggressive weight updates. What word2vec showed was that if you stripped out everything and you skip some steps, yeah, it's an approximation, but it's so much faster. You can train on, was it 8 billion tokens in like 6 hours on a 32 core machine? It's so much faster that it can train on so much more data. That it can gather so much more information that even though, the backhoe is dropping dirt while it's driving back to the dumpster, it can do it so much faster, so many more iterations that it just doesn't matter. So there's a lot of cases where this, we might make it way faster, and then we'll train on 7 times more data, right? And then that'll actually get us to a higher score. And actually, I can almost guarantee you that if we had 7 times more data and we train this, with something that's 7 times faster relative to this, it's going to get a way higher score because, once again, you're covering more ground. We lost a marginal amount of accuracy here. So if training over more data was the problem, then this can often be a really, really good solution. Hope you've enjoyed this section. And in the next section, we're going to talk a little bit more about what's actually happening under the hood in the weights. How are they adjusting each other? What's happening on the terms? And really see some kind of cool visualizations that help us get a more intuitive feeling for what's going on in the neural net. See you there.